Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module named Rutherford backscatterings, generally abbreviated as RBS. This belongs to the paper Characterization of Materials 2. So students, let's see what we are going to learn in this module. First, we will learn about the surface characterization techniques and introduction to Rutherford backscattering. Third, we will study about the scattering geometry and kinematics. Surface analysis is an important part of materials characterization and is important in many ways to know about its properties, including its chemical reactivity, electrical properties of interfaces, corrosive properties, defects and dislocation on the surface. Moreover, the surface of materials can be modified selectively and can be functionalized for specific purpose. There are many important techniques for characterizing the surface of a sample, including Auger electron spectroscopy, abbreviated as AES, X-ray fluorescence, abbreviated as XRF, X-ray photoelectron spectroscopy, abbreviated as XPS, secondary ion mass spectroscopy, and abbreviated as SIMS, and finally the Rutherford backscattering, abbreviated as RBS techniques. Let us go and study what are these techniques and what are the working principles behind these techniques. First, let us focus on AES. The principle of Auger electron spectroscopy is governed by allowing a high energy electron from the incident beam to eject an electron from its inner orbit, creating a vacant space or a hole in the orbit. Due to this, another electron from the higher orbital jumps into and occupies the vacant state. As there is a transition of electron from higher orbit to a lower orbit, energy is released. This energy might eject another electron from its orbit instead of emitting a photon. This electron is called Auger electron. These transitions are characteristic transitions and are used to identify the elements by measuring the energy of the emitted Auger electrons. These transitions depend on initial energy of the incident beam and their interaction with the atom. These interactions include the coupling between spin and orbital angular momentum of electron, and accordingly the energy spectra in each case is analyzed with greater details. X-ray fluorescence spectroscopy. When the surface of a material is exposed to high energy radiations such as X-rays, they become ionized. If the incident radiation is high enough to dislodge a tightly bound inner electron, then an outer electron makes a transition from outer orbital to the inner orbital and replaces it. When this happens, energy is released due to the decreased binding energy of the inner electron orbital compared with an outer one. The emitted radiation is of lower energy than the primary incident X-rays and is termed as fluorescent radiation, as the energy of the emitted photon is a characteristics of that particular element. This can be used to detect the element present in the sample. The analysis of major and trace elements in geological materials by X-ray fluorescence is made possible by the behavior of atoms when they interact with radiation. Another spectroscopy is called X-ray photoelectron spectroscopy and abbreviated as XPS. It is used in analyzing the surface chemistry of a material. XPS can measure the chemical, electronic state and composition of the materials. XPS spectra are obtained by irradiating a solid surface with a beam of X-rays while simultaneously measuring the kinetic energy and electrons that are emitted from the surface of the material within few nanometer of depth. An XPS spectrum is recorded by counting the number of ejected electrons over a range of electron kinetic energies. The peaks in the spectrum are the characteristic energy of that particular element. The energies and intensities of the photoelectron peaks are essential for the identification and quantification of all surface elements. SIMS, secondary ion mass spectroscopy. In this technique, abundance of materials on the surface are probed by sputtering it with a focused primary ion beam, and the ejected secondary ions are controlled and analyzed. The mass to charge ratios of these secondary ions are measured with a mass spectrometer, and the elemental, isotropic or molecular composition of the surface is analyzed. Due to the large variation in ionization probabilities among different materials, SIMS is considered to be a qualitative technique. SIMS is the most sensitive surface analysis technique with elemental detection limits ranging from parts per million to parts per billion. All the spectroscopic techniques described above have some advantages and limitations and are described in a tabular form below. The Auger electron spectroscopy has an advantage of high resolution, but it is a destructive technique. The X-ray fluorescence spectroscopy has an advantage of non-destructive and utilizes liquid samples, but have limitations of low resolution for light elements. The X-ray photoelectron spectroscopy has an advantage of 10% accuracy could be achieved with standards, but has a limitation of destructing the sample. The secondary ion mass spectroscopy has an advantage to detect hydrogen atom isotopes, but it is very complex. Finally, the Rutherford backscattering spectroscopy has an advantage of having non-destructive technique, and the accuracy is less than 5%. The limitation of this technique is it is expensive and an accelerator is needed. Rutherford backscattering, an overview. The Rutherford backscattering spectroscopy is a technique used for the surface analysis of solid samples. In this technique, ion energy in the range of 0.5 to 4 megaelectron volt is used to bombard the target, and the resulting backscattered ion is analyzed by solid-state detectors placed near the target. Both quantitative analysis of the composition of a material and depth profiling of individual elements are possible by RBS technique. It is non-destructive and doesn't require any reference sample for the quantitative analysis. The RBS has a depth resolution of the order of several nanometer and is sensitive to the detection of heavy elements in the order of parts per million. The analyzed depth is typically about 2 micrometer and 20 micrometer for incident helium ions and incident photons respectively. One of the limitations of RBS is its low sensitivity for light elements, which often requires the combination of other nuclear-based methods like nuclear reaction analysis, abbreviated as NRA, or elastic recoil detection analysis. The projectile ions used in RBS include photons, helium-4, and lithium ions at backscattering angles of typically 150 to 170 degree. The underlying principle in RBS is governed by the kinetics of binary collisions. A beam of particles with mass m1 and energy E0 is bombarded on the sample of mass m2, which is the target, as shown in the figure. The energy E1 and the scattering angle theta of the particle m1 are detected after the collision. As the collision is elastic, mass of the target particles m2 can be estimated using the law of conservation of energy and momentum. Furthermore, since the possibility of scattering in a certain angle is known by Rutherford cross-section, it is also possible to estimate the abundance of M2 particles in the same sample by counting the yield of scattered particles M1 in a certain solid angle covered by the detector. Schematics of Rutherford backscattering experimental setup. A schematic diagram of Rutherford backscattering setup is shown in the figure. The setup has a tandem particle accelerator which can produce beams of low mass ions in the mega electron volt range. It generates negative ions which are subsequently accelerated towards positive potential. All the measurements are done in a vacuum system, and at the high voltage terminal electrons are stripped off and the particle become positively charged. Then
they are repelled by the high positive voltage and increase their energy further. The beam is then analyzed and directed to the target chamber. The spot size of the beam is about a millimeter in diameter at the target. When the positively charged ions reach near the target, they experience the Coulombic repulsion due to the nuclei of the target atoms and are deflected from their original path. During this process, some of the projectiles will also be back-scattered and would be collected by the detector mounted at an angle of 170 degree from the incident beam. Note that the number of backscattered ions would depend on the Rutherford scattering cross-section, which would be discussed later. During this process of collisions, there are other inelastic collisions as well, and the incident energy E0 lose energy during this process. A proper knowledge of the incident energy E0 of the projectile and nature of the target would enable us to analyze the depth profile of specimen under study. The RBS technique can be used to analyze several micrometer deep profiles for different targets. The backscattered electrons generate electron signal which is amplified and processed by digital electronics. The output is displayed as a spectrum on the computer screen and hence is called backscattering spectrometry.
Now, let us see what is the basic physical concept behind this RBS technique. RBS involves the scattering of two different particles having different energies associated with them. Accordingly, four different physical phenomena during the scattering need to be taken into consideration. These factors fundamentally influence the outcome of the results which are given below. First, the energy transfer in the process of scattering between the projectile and target nucleus under study in an elastic two-body collision. This process determines an important factor called the kinematic factor. Second, the likelihood of occurrence of the event such as two-body collision. It leads to the concept of scattering cross-section and to the capability of quantitative analysis of atomic composition. Third, the energy loss of ion passing through a dense medium. This process leads to the concept of stopping cross-section and to the capability of depth perception. Fourth, the statistical fluctuation in the energy loss of an atom moving through a dense medium. This process determines the resolution of depth profile analysis in backscattering spectrometry. Now, let us see what are the limitations for this experiment. The limiting condition for designing the experiment in RBS are basically two types. One is RBS is a projectile with certain energy collides elastically with a target atom having different mass and energy than the projectile. During the process of collision, there is an energy transfer between the projectile and target atom under study. By carefully analyzing the energy of incident beam and the final beam of projectile and the target atom, one can estimate the mass concentration and to the depth profile energies of the target atom. In order to achieve this, one needs to be considered the following two limiting cases which need to be taken into consideration while designing the experiment. First one, the initial energy of the incident beam is E0 must be greater than the binding energy of the target atom, which is typically of the order of 10 electron volt. This will enable the scattering process to start effectively. Second, the nuclear reactions and resonances must be absent. This puts an upper limit to the energy of the incident beam. Nuclear reactions generally occur in the mega electron volt range of energy and is dependent on the atoms under study. For example, nuclear effect appears in 1 mega electron volt range of energy for hydrogen ions, while it is 2 to 3 mega electron volt for helium ions.
The scattering geometry and kinematic factor K. The simple elastic collisions of the two-body problems can be solved by equating the energy of the incident and target particle before and after the collision while applying the law of conservation of energy and momentum. Let V0 and E0 is equal to half m1 v0 square, v the velocity and the kinetic energy of the incident particle before collision, and target particle m2 is at rest, half m1 v1 square and half m1 v2 square are the kinetic energies of the projectile and target ion respectively after the collision. The conservation of energy and momentum in the parallel and perpendicular directions require that half m1 v0 square is equal to half m1 v1 square plus half m2 v2 square. Let this be equation 1. m1 v0 is equal to m1 v1 cos theta plus m2 v2 cos phi. The other equation of inequality is m1 v1 sin theta minus m2 v2 sin phi is equal to 0. Eliminating the values for phi and v2 from equations 1, 2 and 3, we get v1 divided by v0 is equal to plus or minus bracket m2 square minus m1 square sin square theta close bracket to the power half plus m1 cos theta whole divided by m1 plus m2, and k subscript m2 is equal to plus or minus start bracket m2 square minus m1 square sine square theta close bracket to the power half plus m1 cos theta whole square divided by m1 plus m2 whole square, where km2 is equal to k, which is equal to E1 divided by E0, is generally called the kinematic factor.
So students, let us summarize what we have learned in this module. First, the Rutherford backscattering is a non-destructive surface characterization technique. Second, it involves the elastic collision of two spaces such as projectile and target, and the energy of the incident and backscattered beam of ions are taken into account to calculate the concentration and depth profile analysis of the target. The kinematic factor K is important in the quantitative estimation of concentration and depends on the energy of the incident ion beams.